All right. Hello, everyone. Uh, let's begin this seminar. The participants have stopped rolling in, so we'll go ahead and open this seminar. Welcome, everyone, to this Catch Science seminar organized by myself and Hélène Agneau under the excellent leadership of Jesse Cremian and Paul Ziegler. Catch, for those of you who don't know, is all about fostering and facilitating interdisciplinary research at the international level with the aim of understanding the natural systems that control atmospheric chemistry and physics and dynamics with a specific focus on these processes that are unique to the cold regions on Earth. Basically, the cryosphere, and this could be from the Arctic to high altitude regions, which we'll hear about today, to the Antarctic. And here's just a little bit of a schematic from Jenny Thomas's paper that goes into some more details. Really Catch focuses on everything from air quality for indigenous peoples that are affected by these natural processes, but also increased anthropogenic emissions due to resource extractions. And then really diving into the oceans with linking biogeochemistry and biology to the exchange processes that exchange gases and aerosols from the ocean through the sea ice and open leads to the atmosphere, and then how these atmosphere aerosols affects clouds and then are deposited back onto the snow and ice and are preserved in these ice cores, but also these chemical exchange processes on the snow and at the micro scale interfaces between these. So today we're going to hear about some high altitude particle dynamics from the global south from Diego Aliaga from the University of Helsinki and the particle physics laboratory in Bolivia. And he's going to give us a nice overview of some of the work he did in his PhD, which he will defend later this month. So, Diego, with that, I will hand the floor over to you.
Thank you, Jacob, and thank you for the invitation for the seminar. So let me share my screen. All right, do you see it?
Not yet.
Not yet. All
There we
right.
go. We're good.
Oh, I
Okay, perfect. Yes, so thank you, Jacob, and hi to everybody. Thank you for joining. So today I'm going to be talking about high altitude particle dynamics in the Andes and with special attention to impacts from volcanic, marine, Amazonian, and urban sources. This is, of course, research done in collaboration with many co-authors. And as Jacob said, I am a PhD researcher at University of Helsinki, soon to finish. Okay, so a brief outline of what I'm going to be presenting today. First, it's going to be an introduction to the Chacaltaya station. Then I'm going to be mentioning the work that we have done in atmospheric transport modeling, because it's a big part of my PhD research project, but also because it's very important in this region of complex topography. And then I'm going to move to the results, and these are going to be mainly focused on impacts from volcanic, marine, Amazonian, and urban sources. I'm going to talk a little bit about DMS and isoprene oxidation products that we observe at the station. Then I'm going to spend a significant amount of time in new particle formation, because I have spent a lot of time of my PhD research on that. And then also I'm going to mention volcanoes and MPF in the context of long-term observations. And this is an ongoing work that I've been doing lately. All right, so let's start with the Chacaltaya Gauss station. So as you all know, it is in South America. It is very high at 5.2 kilometers above sea level. Here in the figure, you can see the elevation lines along the continent, and the red dot is Chacaltaya. And basically, it's in the interface between the Amazon and the Altiplano. Specifically, it is not at the top of Mount Chacaltaya, but 200 meters below, and it has an open view to the west. So this is a picture taken from the top of Mount Chacaltaya, and the observatory is down there. So what we do, or what we measure, and why it's relevant. We measure long-term climate relevant gas measurements. For example, the CO2 concentration here showing this increasing trend that we observe throughout the world. And here we don't see this seasonal variation so much because we are in the tropics. We also measure long-term aerosol physicochemical characteristics. And then here I'm showing equivalent black carbon that does not show a clear trend, but it has a clear seasonal variability, which is driven by biomass burning in the Amazon. And why we measure it, one of the main arguments that I can make for it is that because nobody else is doing it in the continent. And to illustrate this idea, I am showing here all of the operational global atmosphere watch stations in the world. And then I have drawn three equal area disks around it. And in Europe, we have 171. In North America, 42. And in South America, 4. Out of these 4, only 2 measure continuously. And that is the Chacaltay Station and the Ato Tower in the Amazon. We also do short-term intensive campaigns at the station. And I want to mention the Salteña campaign that we did in 2018, and it lasted for 6 months. Most of the results are the product of this campaign, and also it was a big part of my PhD project. And just as an illustration here on the top is the station under normal conditions, and then here is during the Salteña campaign, when we basically were at the limit of the energy that the station can provide. Okay, so now let's move into the key source regions and the emission drivers. And let's focus in the Chacaltaya area. So basically, what we have observed there throughout the measurements is that we have Pacific influence, basically biogenic emissions, dimethyl sulfide. We also have influence from the Amazon, and then the drivers there are biomass burning, but also biogenic emissions from volatile organic compounds. And then we are also influenced by the urban area of La Paz El Alto, that it's nearby Chacaltaya, 20 kilometers south and 1.2 kilometers below. And the main driver there is traffic emissions, basically fossil fuel combustion, which is a bit different there because of the high altitude. You have incomplete combustion. And then finally, the Altiplano, which is the big chunk here in the center. And I think that the main driver there can be argued that is the volcanic degassing, even though it's sparsely populated, and also you have some farming going on there, small scale farming. Okay, so what are the atmospheric transport patterns that we observe there? This is a very, very simplified schematic. So we have the station there on top of Mount Chacaltaya, and then we have the boundary layer in the Pacific, in the Altiplano, and in the Amazon. And basically, the general circulation pattern is driven by the westerlies during the austral summer when the ITZZ is shifted southwards, and then during the austral winter, it is also driven by the ITZ, but then in this case, it's shifted northwards, and then you have the easterlies. But I mean, reality is much more complex than this. And in general, you have many more interactions between the boundary layer and the free troposphere. And a simplification that we usually do when we measure at these high altitude sites is that we are in the free troposphere. And I think that this is not correct because, I mean, by definition, we are measuring at ground level. We are in the boundary layer, in this case, the mountain boundary layer. However, under certain conditions, what we measure there is representative of the free troposphere. And on the other hand, under other conditions, what we measure there is representative of the boundary layer nearby. Now let's talk a bit about high resolution atmospheric transport modeling. And I'm mentioning this because it's very important to know the air mass history of the air masses that we sample there, because it's a complex topography and it's the only way that we can inform the composition that we are sampling. So for doing this, I ran this regional meteorological model, WRF, and I did it with 4 nested domains. And The reason for this is that I really wanted high resolution in the inner domain. I went 1 to 10 kilometers, and then you need to do this gradually. I use the output or the meteorological output from this to run a transport model, in this case FlexPart, and I run it in backward mode, so basically tracking the air mass history. And this is a very simplified result of the output. The color intensity is the SRR, or source receptor relationship, and in very simple terms, when you see a pixel that is very high, it's telling you that if you would have emissions there, it's very likely that they would have a high impact at this station. I have spent a lot of time into simplifying this very massive output from the FlexPart into a very concise and easy to use time series of the source regions. And for this, I have used advanced clustering techniques. And a result from this study is, for example, that the surface impacts the station very often. In this plot, in the x-axis, we have the time of the day. In the y-axis is each individual day that I model, and then it's color-coded by the influence from the surface. And the general pattern that we see there is that at noon, we have influence from the surface nearby, but then that during the night, we have little influence. But this pattern is not followed all of the day. So you have times where you would have influence throughout the day and days where you have no influence during the day. So it's very important to keep track of this influence. So moving on to the results, I'm gonna now talk about the marine influence from the Pacific and in the context of DMS oxidation products. And in terms of the transport pattern that we observe during this influence, it basically comes from the easterly, is transported in the free troposphere, is long range, and probably it has been in contact with the Pacific surface very, very far, not near the Pacific coast. In terms of what we measured or how we detected this influence was basically using the PDR3 SIMS. And what I'm showing here is MSA, it's a primary oxidation product of DMS, and it is shown in orange. And what we notice is that we had peaks during many days, but these peaks do not happen every day. And when they do happen, they happen early in the morning. And by contrast here, I'm also showing oxygenated aromatic compounds, and these are kind of a proxy for anthropogenic emissions nearby, and they kind of anti-correlated with the signal of MSA. So we took a very detailed look at how the air masses were behaving during these days. And then, for example, I'm going to show here what happened during the 11th of May. And the transport pattern during this day was definitely from the Pacific. And this represents the transport pattern throughout the day, in the morning, but also early in the morning, but also during the day. In terms of how this looks vertically, what we notice is that it is transported very high in the atmosphere. And then as it gets closer to the station, it goes down here. As a reference, the black is the topography. So basically, this is the altiplano. And then the blue line is the most probable particle trajectory. Then the next question is, okay, so if this is how we observe throughout the day, then why do we observe MSA early in the morning and not later in the day? And for that, we need to actually look at the close range influence, and that's what we did here. So basically, these are the transport pattern 100 kilometers before we arrive to the station, and that we see is that early in the morning, the air masses are really being transported horizontally above the potential boundary layer and with little influence from the surface. By contrast, later in the day, the pattern changes, and then we have influence from the surface, likely driven by upslope thermal winds. So to summarize this study that was led by Bibik, Stoltz, and Yali Shen, we observed long-range transport in the free troposphere from the marine environment. It is the first comprehensive measurement of DMS oxidation compounds at this altitude and distance from the sources. It provides insights into the behavior and fate of DMS in the free troposphere. And in terms of new particle formation, what we notice is that it has little impact on the particle composition. And this is mainly because when we do observe new particle formation, the signal is driven by the influence from the altiplano. Now let's move a bit forward to a different influence, in this case, the Amazon, and we are going to be discussing the isoprene oxidation products that we have observed there. In terms of the transport pattern that we observe here, again, it comes from the Amazon, but it has a different vertical and horizontal shape. So basically, it goes vertically in the Amazon and then horizontally is transported to Chacaltaya. And then a schematic of what we think that we saw there is perhaps better displayed here. Basically, we have isoprene emissions in the Amazonian forest. These are transported vertically in mesoscale convective systems. Up there, they are mixed with OH, HO2, and NOx that is generated from lightning. And then they are deposited in the free troposphere, where it's very cold, and likely under transport to Chacaltaya that lasts around 30 hours. These isoprene oxidation products can participate in the early stage of new particle formation growth. And then finally, when we measure at Chacaltaya, this combination of isoprene organic oxidation molecules and ultrafine particles. How does this look in the observations at Chacaltaya? Here I'm selecting one day of the 11 days that we had during this study, but the pattern is similar. And basically what I'm showing here is C45 compounds, C68 compounds, and C9 compounds. And C45 compounds are non-oxidation products of isoprene. And then C68 and 69 are known oxidation products of anthropogenic emission. So the idea is that if you see all of them increasing, then likely you have anthropogenic influence. But if only C45 is increasing, then it's likely coming from isoprene oxidation from biogenic sources. In terms of the ultrafine particles, what we observed during these times is that they also increase. And when I say ultrafine particles here, I refer to 10 to 15 nanometer particles. And then in terms of indicators of being in the free troposphere or boundary layer influence, we can look at the water vapor mixing ratio, which consistently show a drop during these time frames. And also EBC, which is a proxy also for anthropogenic pollution, was in the detection limit of the instrument. If we look at the transport modeling that we did for that specific time period, what we see is that effectively the air masses are coming from the Amazon. And if we look at the vertical component of the transport, we see that effectively it was originating in the surface, 1,000 kilometers away from the station, likely went into horizontal deep convection and then vertical, and then transported horizontally to the Chacaltaya station. In terms of the significance of this result, it was the first experimental evidence of oxidized organic molecules contributing to MPF in the tropical troposphere, and we did this with direct chemical composition measurements. Okay, now let's shift gears a bit to new particle formation. And this is the latest paper that I have published. And I'm going to spend some time here because I have also spent significant time of my PhD working on this. And I'm going to first focus on what we see when the air masses come from the Amazon. So basically, this is the pattern that we think is happening. Rather than being convected in this deep convective system, it goes along the surface and reaches the station. And for this study, we have 65 days. And 22 of these 65 days follow the pattern that I just shown from the Amazon. How does this look in the measurements? It is shown here, and let me explain this graph a little bit. So in the x-axis, we have the hour of the day. The blue line is the median of all of the days that follow this pattern, so these 22 days, and it's I do the median at every hour. Just as a comparison, I also show the gray line, which is the median of all of the days, so the 65 days. And what we see during these days is that basically BC is very low by comparison in terms of the uh, particle number concentrations. They are also very low or very clean. And then in terms of new particle formation, the formation rate is very, very low by comparison to the median. Sulfuric acid also is low in comparison. And finally, the condensation sink, which is another indicator of having aerosol particle surface area, it's low. And I guess one point that needs to be addressed here is that are the clouds above or below the station? And in this case, I think that we have strong indicators that they are below the station. We do have cloudy conditions, but we still would, if we had the proper ingredients for new particle formation, we still would have enough photochemical activity with these levels of incident shortwave radiation. And when we look at the transport patterns during these days, we notice that they effectively come from the lowlands in the east, the Amazon on the north, and also the Chaco area. But I mean, just for generality, I'm going to call it the Amazon. And then again, this is the process that I was describing before. Now let's move to the urban sources, again in the context of new particle formation. And the transport pattern that I observed during these days is basically this direct influence from the polluted environment in the nearby city. And I'm going to spend some time here describing how we detected this influence. And for that, we're going to look again at the transport modeling that we did in the region. And just quickly, here is Chacaltaya. Here is the El Alto La Paz urban area. I want you to ignore the gray blobs and just focus on the red blobs. And basically, they are markers for where the air masses were 4 hours before they arrived to the station. And the size of these spheres is related to the influence of the air mass in that region. And then, so this is what happened early in the morning. And then when we shift towards noon, what happens is that we have a very significant component of the air masses coming along the surface from the direction of the city. And then finally, at night, what we see is that the pattern is again shifted and the air masses are now coming rather from the east. How does this look in the measurements? Basically, the concentration of black carbon is very high, especially compared to what we measure as the median of all of the days. In terms of new particle formation, we do observe nucleation and growth before 12, but then after 12, we see this intense mode in the larger sizes. And then in terms of formation rate, we see increased formation rate before noon, especially compared to the median, but then it diminishes after 12. Sulfuric acid increases before 12, but then it just drops down. And this makes sense in the sense that we don't expect any emissions of SO2 in the city. In terms of the condensation sink, it follows basically the pattern of black carbon. And then again, the incident shortwave radiation follows a pattern that would indicate that there were not many clouds above Chacaltaya. So now let's move to the altiplano. And here I have also added volcanic altiplano. And then the connection between the two, it's a bit complicated, as I'm going to explain later. But let's focus on the pattern that we observe here. So basically, it's coming from the altiplano, and it is in this mix of boundary layer free troposphere, and we have little influence from the city. How does this look in the measurements? Basically, we see not much influence from BC, very similar to what we see in the median of all of the days. In terms of new particle formation, is like this textbook perfect banana shape event where we have nucleation and subsequent growth. In terms of formation rate, it's very, very strong, especially compared to the other days. And then sulfuric acid is also higher than the median of the other days. In terms of the incident shortwave radiation, it's a perfect clear sky day, and the condensation sink follows a different pattern than the rest of the days, and this is because at this point, the particles that have been newly formed have grown to a size larger enough that they have an influence in the condensational sink. Finally, let's move to, again, the altiplano influence, but now when we are under the direct influence of volcanic degassing. So we suspect that we are in the plume of degassing that has happened recently. Why do we think that this is happening? We can look at the sulfate mass concentration that we observed during these days, and then we observe that by comparison is very, very high, especially compared to the other days. In terms of new particle formation, we do observe it happening, but then the intensity of the events are significantly diminished compared to the rest. So now it peaks at 1, whereas when it's from the altiplano without the direct volcanic influence, it's around 10. So it's an order of magnitude reduction. In terms of sulfuric acid, and here is a bit surprising, it's very, very high. So even though we have a lot of sulfuric acid, which is a precursor for new particle formation, we observe very, very low rates of this. And one could think that because we have a lot of sulfate, then the condensation sink is increased, and this would explain why we don't see it. But in reality, the condensation sink at its top is comparable to what we see during the other days. In terms of the incident short-wave radiation, we do have clouds, but again, they are not significant. What we think is happening here, and we need to do further investigations on it, is that because we have so much sulfate in the particle phase, the aerosol becomes acidic, and then all of the ammonia that is present in the gas phase is basically eaten by the aerosols. And then we enter a ammonia-limited regime. And we know from earlier studies that the main mechanism for new particle formation in the region is sulfuric acid ammonia. Okay, so now let's move to volcanoes and new particle formation. And this is a different study that I'm working on now, and it's from a long-term perspective. And basically the main result that we have so far is that volcanic degassing enhances new particle formation intensity in the Andes. And I know that this is a bit contradictory because on one hand, I'm saying that when we are under the volcanic plume, we see reduced new particle formation, but then here I'm saying that volcanic degassing enhances new particle formation. And I think that the key parameter here is that volcanic degassing would increase the background concentration of SO2 in general, but then when you have the degassing event itself, then it will decrease. So here we first try to look at what are the hotspot emission areas in the domain. For that, we use the integrated SO2 column. We did a 20-year analysis, and the intensity is shown in shades of red. And basically, there's only one hotspot in the region, and it's here. And then it's comprised of 3 emitters, the Sabancaya volcano, the Ubinas volcano, and the Ilo, which is a smeltery. And then next, I wanted to look a bit closer at this hotspot of SO2. So I looked at the time series of the emissions of each individual component. And what I see is that the Ilo smeltering early in the Salarat area was a very big contributor, but then around 2008, it completely went down after they installed some filters in the chimney. And then we had a couple of years where we were in this very low SO2 environment. That stopped around 2013 when Ubinas started an active degas phase. And then after that, Sabancaya took over and also entered an active degassing phase. And in a way, what we have here is a very nice natural experiment because we have measurements from 2012 to 2023, and we have a big period where we had very little SO2 emissions, and then later on we had higher emissions. But then just because we have emissions on one hand, and then we are measuring on the other side, it doesn't mean that we are gonna actually measure it. We need to have the right transport conditions in the atmosphere. And this is what Laura Ticona focused on. So she did this very long-term analysis of the influences of the air masses. And what she found is that basically Chacaltaya is mostly influenced by westerlies during the dry season with a peak in May. That goes almost to zero during January. She did this with this 11-year back trajectory clustering analysis, and then again the main conclusion was that 60% of the influence from volcanic hotspot comes in May. Then the next step that we did is that we started measuring SO2 when we discovered that it was a volcanic influence was potentially important, and we started measuring in 2019. So we are trying here to get a puzzle of different measurements at different periods. And Christoph worked on this SO2 time series, and basically what he did is he divided the measurements into two regimes, what he called the background and the plume regime. And I want you to focus here on the solid line. So the blue solid line is the concentration that we observed during the background regime. And then the solid orange line is the concentrations that we observed during the plume regime. And basically what this plot is saying that during the wet season in January, in general, we have most of the time we are in the background conditions. And sorry, this is shown by the thickness of the shaded area. So basically, the thickness tells you how much time you are spending in the background or the plume area. So basically, in summer we spent around 100% of the time in this background regime, and then in the dry season in winter we spent up to 50% of the time in this plume regime where the concentrations are above 1 ppb. This pattern is repeated throughout the years that we have measured, except for the last year. And we don't know what happened there, but it could be that the transport patterns were influenced by El Nino, which was quite intense during that year. And this again is a reminder of the westerly influence throughout the year. So corresponds quite well with the plume conditions. So just to summarize, the observation period was 19 to 24, and then the plume conditions, 60% of the dry season, and in the background conditions, the concentration was below 1.1 ppb in general. And then on average, he observed that we have 2 plumes per week. The duration is more or less 13 hours, and then the median SO2 is 0.32 ppb. Okay. So finally, I think that this is the result that ties everything together in this long-term analysis, and this is what Sarela did. And basically, she looked at formation rates from the period 2012 to 2018. So this period shaded in this area. And then what she did is she related the emission rates that we observed from the satellite to the observed monthly median observed formation rates. And she used basically only the months that we are when we are in the dry season, because that's when we have the influence from the west, from the west. And basically what she has found is this very strong positive correlation between the emissions of SO2 and the formation rate. Basically in the dormant period in 2012 and 2013, formation rate was around 10, and then at the peak of the active period in 2017, the formation rate was around 25, so 2.5 times higher. All right, so now some takeaway messages. We did detailed transport modeling, which is needed to inform analysis, especially in this complex terrain. The station is strategically placed and it's influenced by various regions, including long range. We observed DMS oxidation products. And then we also did the first observation of evidence suggesting biogenic MPF from isoprene oxidation products in the Amazon. Then in terms of new particle formation, we observed that the strongest MPF happens when air mass arrive from the altiplano and they have limited city influence. We also found that the volcanic influence likely drives strong MPF, but it is suppressed during the plume conditions. And we think that this is because we are in an ammonia-limited regime. And then in terms of the long-term volcanic influence, SO2 in the region mainly originates from volcanic degassing. The plume conditions are prevalent during the dry season, and then finally enhanced volcanic SO2 degassing leads to higher MPF. Thank you. That is it.
All right. Thank you very much, Diego, for that excellent presentation. Very, very nice. Really cool stuff you were showing there. I always like it when I've read some of the papers and then I still learn something new in a presentation. That's really nice.
Thank you.
Do we have any questions from the audience immediately? Feel free to unmute yourself, turn on your video, or raise your hand or anything. If you don't feel like speaking, just shoot it in the chat and I can read it for you. Or everyone can stay silent with their videos off. That's also fine. So Diego, maybe some of these contradictory results you were talking about. Volcanic degassing increases the background SO2, and then this very acidic aerosol depletes all the ammonium. But if I was not mistaken, you still had some NPF on these days. And so can you just speak more about some of these contradictory results of the volcanoes limiting NPF on these plume days, and then increasing it in the long term? Just you explained it very nicely, but I think it took me a little bit to wrap my head around it.
Yeah, I think that that's a very good point. Something that I didn't show about it is that, I mean, we have also done measurements at the city during the same time, so during these volcanic events. And something very interesting that we found there is that basically there is no difference at the city in the formation rates between the days when we have influence from the altiplano and when we have influence from the altiplano plus the volcanic plume. And if we advance the hypothesis there that base stabilizer, so the absence of is what is driving this diminished formation rate at Chacaltaya, then the reason why we don't observe this diminishing formation rate at the city is because we have there direct emissions from urban pollution. So that would be basically amines. So that would be an indicator that maybe we are in this base limited regime. And I think that, I mean, so we still see new particle formation, right, during these volcanic events. But I think that it is reduced basically because the availability of ammonia in the vapor phase is also reduced. Probably not completely depleted, but then once we are lacking it, then we don't have enough ammonia to stabilize the clusters.
Yeah, okay. That makes a lot of sense. And I guess I'm just thinking it's not exactly diminished, but just reduced, or not, removed, but just reduced in intensity
Yeah,
would be my thinking instead of it's completely shut off.
yeah. I mean, I think that this is a very good point, and I mean, and it's very hard to answer because we don't have direct measurements of ammonia there, and it's very difficult to measure ammonia, right? Although I know that Matt Boyer is now measuring it quite well. Hopefully, we can bring the instrument there. But what we have trying to do is to have a proxy indicator of the ammonia levels that we would observe there based on the chemical composition of the aerosols there. But yeah, I think that it, I really don't know if we completely reduce the, like if we completely get rid of the ammonia or if it's just reduced.
Okay. We have a question in the chat from Isabel. Very good question for your PhD defense, because this is something I think I've heard. I got asked it and everyone got asked it. So first off, she says very clear presentation, and at a good speed. And so her question is, if you had unlimited resources, time, money, planning, etc., and you could go back in time, what would you have set up an extra station during the campaign? What instruments or maybe what other, maybe some vertical measurements, anything, what else would you have done differently?
Yeah, I mean that is that's a very nice question. Um, I think that oh, if I had unlimited resources, I would measure everywhere. But if I have some limited resources, but still I can measure somewhere else, I think that it would have been ideal to measure in the middle of the altiplano when we are not influenced by the city. Because that is, when we are comparing these two measurements during the Sartenia campaign, the problem is that we are not only changing one parameter like altitude, we are also significantly changing the chemical environment because we are in the city. So basically, we don't have any idea of what are the formation rates in the, let's call it altiplano background conditions. And I think that it would be very, very nice to have an idea there what happens there. If I had even more money, I would like to have a station on the western edge of the altiplano because then we could also answer other questions. For example, if during the wet season we don't observe MPF just because the air masses have not spent enough time in the altiplano to get this extra SO2, or is it really something happening with the air mass coming from the Amazon? Um, yeah, I think that that would be my short answer.
I think you answered her other question. She asked, "What about other mountains?" I don't know if you read it as you were speaking or something, but
No, I didn't, but yeah.
you answered it right, right after she asked it. So very nice. So you were just talking about in the other mountains and during when they were coming from the ocean, you didn't observe any NPF in marine air masses.
Yeah. Um, yeah, no, we didn't. And I think that because the periods where we observe these marine free tropospheric air masses are very, very short. Um, and then we did not observe an increase on the population of the ultrafine particles, if I remember correctly. And then, of course, during the day, we do have this marine influence, but then the signal is completely overdriven by emissions from the altiplano. Does
Oh,
that make sense?
yeah, yeah, yeah. Okay. I was just thinking, you see this nice MSA signal, and then obviously sulfuric acid would be produced too from DMS. But then if they're coming over the anthropogenic cities, maybe the condensation sinks too high or too not enough precursors to do MPF, and then
Yeah, I guess that, yes, we have this very nice signal of MSA, but it's very low, right? Because
okay, very
it's
low.
not in the detection limit, but it's very low because we are far, far away. Um, I think that that can be one more plausible explanation. Um, but yeah, out of the 65 days that we had there, there was only one day when we actually saw sulfuric acid there during the day that was linked to also an increase of MSA. And there was some indication that potentially there was a mode in the ultrafine particle, but I don't think that it was conclusive. And I think that just having one day where this happens, we did not explore that.
Makes sense, yeah. Any questions from the audience? No. Um, Diego, what are you going to be doing for your postdoc?
Um, Taking vacations. No, so I'm gonna continue to work at the at results from Chacaltaya, but I'm gonna focus more to the long-term aerosol measurements, and I'm gonna be combining those with model output and trying to investigate if the um, dynamics that we observe at Chacotaya in terms of the aerosol changes are well represented in the models. So I'm gonna look at several models, and then one of the ideas that we are advancing now, but we need to carefully check if it makes sense or not, is we're gonna try to see if the aerosol size distribution and loading is sensitive to different intensities of El Niño. So basically, we have these 12 years, and then El Niño has been uh, happening at different intensities, and then we want to see if really there's a change in the patterns, and then if these changes have any feedback effects, and then if it's only transport or also the emissions changes. So that's going to be one of the other projects that I'm going to be looking at.
Okay, very nice. Sounds very interesting.
Let's see how it goes.
Uh, yeah, I don't have too many other questions. I don't think anyone else does. I'm sure your postdoc will be really great. I think it's cool you do a continuation of your work. I look forward to hearing some more interesting results from Ketchatayo.
Yeah, thank you. Yeah, I'm actually super happy with the project, and then also to be uh, linked still to the Chacaltaya station, which I mean it's been a significant part of my research, and then I really like to do more science in that area.
Well, look forward to it. And with that, I think we can go ahead and conclude this seminar. I'll just thank you once again, and good luck with your PhD defense.
All right. Thanks a lot, Jacob, and thanks a lot for the invitation. This was a super nice experience and also a very good preparation for my uh, defense that is coming soon.
Absolutely. Thank you, everyone from the audience for attending, and we'll see you next time.